Nidhi Raniyar. Nidhi is a software engineer with expertise in ML and artificial intelligence and holds a specialization in machine learning and data science. Nidhi, please welcome on stage.
Hello, am I audible? Okay, mic check, hello. We good? Okay. All right, so unlike most of the session, I think this is going to be slightly more technical. So, yes, bear with me. Before I start, I would like to get a feel of how the room is. All the students, can I have a hand? People who are still in college? No one? Okay, amazing. All the people with less than 5 years of experience here? Okay, people with more than that? Okay, amazing. How many of you are in data science or ML or somehow related to the field? Yeah? Okay, amazing. Thank you. I feel like I'd rather know who I'm talking to before I start talking, so that makes sense? Right. So I would want this to be a little bit more interactive. This was supposed to be a classroom session, so I'm going to treat it as a classroom session, okay? So how many of you believe in astrology? We're all women of science here. No astrology people? Okay, amazing. Even I am not. But I'm sure at some point of time you would have seen someone, heard someone go to an astrologer and how they work, right? They will look at your palm or look at your face or look at your kundli and tell you what kind of a person you are, right? You're shy, you're talkative, maybe you're bold in life and things like that, right? Now that is pretty much not backed by any kind of science. Handwriting analysis or graphology is something very similar. So by looking at your handwriting, I'm sure if you have ever taken a psychology class, by looking at your handwriting, you can tell what emotions the person is going through. If you ever have taken therapy or have gone to serious counseling, they will make you write things and draw things, not just to understand what you're thinking, but also to understand how you're writing it and why. So the pressure of your pen, the slant in your handwriting, the pressure with which you put the dot on top of an I, all of that together will talk a lot about your personality. I have this senior, my mentor Manjeet. He was supposed to be here with me for this presentation, but unfortunately he's not feeling very well. But he's gone through a year of training on how to analyze handwriting, and that's where this entire project's coming from. Also, I would also like to talk about why this project and how this project came to existence. Now, IBM does a lot of mentorship projects in collaboration with a lot of colleges. One similar college is IIIT Bangalore. We have been, we've published a lot of papers and we've worked on a number of projects with them. So the entire project is about taking different aspects of your day-to-day life and figuring out who you are, right? So handwriting is one part of that. The entire project also entails on speech recognition, emotion recognition, how you talk, how you walk, everything. So you do a complete recording of, or maybe a vlog of your life, you upload it, and they're going to do an analysis on who you are as a person, right? So that's the entire project. This is one small piece of that. And I think in a half-an-hour session, that's the maximum I can talk about. So we'll start with handwriting analysis. So good afternoon, everyone. I'm here to take this session on enhancing handwriting analysis with DenseNet-169. Anyone here who's worked with or heard of DenseNet-169 before? Yeah? Okay, so it's a convolution neural network, that's it. If you must have studied CNNs. It's one of the forms of CNN. It gets a lot of data from the previous layers, and then all the previous layers feed into the data for the next layer. So that is what DenseNet-169 is. Eventually, I'll talk about why we are using DenseNet-169 here. We also have an explainable AI over here. A lot of people question why did AI come up with this solution. So we are also going to answer that. Being a part of IBM or working with the machine learning side of IBM, I've realized one thing. The one thing that differentiates IBM working in machine learning is that we focus on AI explainability and AI responsibility a lot. So yes, I'm going to give you the prediction, but I'm also going to give you a very detailed explanation of why that is happening. So this project also entails on why did we come up with this entire idea of, okay, your handwriting is makes you feel like you're a bold person, you're an extrovert person, you're an introvert person. All right? So let's start with the part one. To begin with, let's look at why handwriting analysis is such a challenging problem. Handwritten text comes in various styles, and factors like image quality, the size of the image, the way image is clicked, if the paper is A4 or smaller or larger. To address this, we proposed a deep learning approach to streamline the analysis of the handwriting. The solution incorporates DenseNet-169 architecture, which is a powerful convolution network, a convolution neural network. And also we have something called as LIME. We'll talk more about LIME later. There is a two-part machine learning pipeline given in this solution. Before that, I would like to give a shout out to Manjeet, because he was the one who came up with the entire idea, and also the students of IIIT Bangalore who've been working on this project as well. Okay, let's move on. So the two-part pipeline that we have here: image validator, pressure determination. So what we're trying to do is first validate the image. Have you uploaded a picture of your dog or an actual handwriting, right? So that is what we do first. We classify the handwriting into valid, invalid, or zoomed. So valid, again, is like a normal standard handwriting on an A4 size sheet with the correct margin and everything. Invalid is a picture of maybe you, your dog, your house, anything like that. We don't want that. And there is another part called zoomed. So it creates a lot of difference on what size you're writing in. If it is a ruled paper, if it is an unruled paper, if you have zoomed into your sheet and clicked the picture. So that's why there's a third classification called zoomed. Now, why did we classify it as zoomed? So that we can run pre-processing on all the zoomed images, make it compatible with all the valid images, and then run through the pipeline, right? Now, the other part is pressure determination. Now, we classify handwriting into low pressure and high pressure. So when you're writing, the depth of how much your pen inks on the sheet is going to determine how low pressure or high pressure your writing style is. Because I think one of the biggest factors when you're doing a graphology is the pressure of the pen you're putting through. So that is determined, that provides insight to your writer's emotional context also. If you're mad, you'll be like cut, cut, cuss. And if you're normal, if you're happy, if you're emotionally stable, you'll be taking your time. You're not in a hurry, you'll be taking your time. You'll be light with your pen. So that is the second classification we have. Okay. I don't know which one is forward and which one's backward. Okay, yes. Now we talk about the DenseNet-169 convolution neural network. With DenseNet, we allow each layer to receive inputs from all the previous layers, okay? Now, how did we come up with that exact number of 265 layers and 265 nodes that we're adding? Again, it was a lot of trial and error. I feel like every time I've built on a project, and every time I've built on any machine learning related project, this question always comes up: why did you pick this number for your number of nodes and your number of neurons? It's never that easy. I feel like everyone goes through at least 10 iterations of doing it with 50, 60, 100, 200, and then whichever gives you the best accuracy goes through. Sometimes it's just as simple as that. You try, you figure out a solution, you don't. So next time, or eventually whenever you're trying to build something in machine learning and you don't know what number to put a random number. Start doing binary sort with those numbers. This works, this does not work, maybe we'll find something in the middle, right? So that's how we came up with all the numbers. This was also pre-trained, so the weight came with a maximized feature extraction capabilities and everything. Okay, pre-processing and augmentation techniques. Now, like I said, we had a zoomed-in picture and we had a valid picture. So first of all, the first pre-processing step that we pulled is take all the zoomed-in pictures and make it compatible with all the normal-sized pictures, right? So that happened. We normalized all the intensity, color-coded it, made it black and white if it was a colored paper or things. A lot of, I think there's like an in-detailed explanation of what went down into that. But mostly the things that are worth speaking about is color. First of all, we made all the red and blue and black pens go away and made it in monochrome. Second is the pixel intensity, because different camera lenses give you different pixels, so we wanted to normalize that. We ensured consistency in image size aspect ratio, and we had a data augmentation method like rotation, noise addition, all that. The data set that we used, let's talk about that. So since it was a college project as well, we just passed around sheets throughout the college, made them write a specific paragraph, took those sheets back and clicked a picture, right? Because we had the capability to do that manual work. Most of our handwriting data set came from the students there, but to add more diversity into it, I mean, at the end of the day, all of those are students from a specific college, from a specific location, which can probably induce a lot of bias. So to remove that, we also combined it with IAM handwritten data set. It's there on IEEE pages. You can go ahead and look it out. So these two data sets together were processed, pre-processed, and used for our data, used for training. Yeah. Yes. So when you look at the color intensity of that, okay, there is a difference between having a red and a black ink and having a lighter intensity of black and a darker intensity of black, right? So say you have a circle, right? The center of the circle is maximum color. The sides of the circle are lighter colors. Now the difference between the outside and the center will tell you how much pressure that is. Now that is how it should technically happen if you're writing a manual script, right? If you're putting putting logic behind it, that, okay, I need to figure out how much pressure there is, that's what you happen. When you end up using things like DenseNet, convolution networks, things like that, it's a black box. You put in data, you put in like a lot of data, and it will tell you if the pressure is there, how much pressure is there, how much pressure is not there, right? So that's how we went about it. So when you're taking a picture of a page, say the page is lined. So we need to first remove the lines, right? It's supposed to happen that way. We did not. So that was kind of the noise that we had already. So lined papers and unlined papers, we had to figure out that. More noises are more like pen shades left on the left side, or maybe your hand imprints on the right side, things like that, okay? Those were the noises. The noises that we induced was something called as albumation. I'm forgetting the term for that. 1 second. Albumentation. So what it does is, it takes your images, it will take your entire picture, it will take one small portion, change the pixels just slightly, and it will basically expand your entire data set. Okay, so you have basically, if you have a data set of 10 pages, it will read those 10 pages, create a little more data set, and add on to it. That, again, is induced noise as well, right? So there is that. Okay, image validation is done. We're at pre-processing. So we had normalization and resolution adjustment for pre-processing. We had data augmentation through the albumination, that word, albumination library. It artificially expands the data set. This includes transformation like rotation, scaling, and noise addition. So noise addition, again, comes with your albumation. It improves the model's ability to generate and prevent overfitting also, right? Okay. Now we're coming to the explainable AI. One of my favorite things because I would want to know why, right? I would want to know why. So Lime is an exciting aspect of this project. It is the integration of explainable AI through Lime technique. Now Lime stands for Local Interpretable Model Agnostic Explanation. Please don't quote me on that. I am bad with remembering terms. I can use it, I can probably not remember it, okay? So I'm going to refer to a page to read it out to you. So local interpretable model agnostic explanation. With Lime, we can visualize which regions the image was most influential to the model. So suppose I have a page of handwriting. Suppose this is a page where I've written things down. Now, if it is extracting the pressure from words over here and not from the words in front of me. So what Lime will do is Lime will highlight this part of my page and be like, okay, this was the most influential part of your image. Think about it, think of it like this. Say you have an image of a cat. So whole page, you have an image of the cat in the center, right? The rest of the white light does not create such a big influence on your entire project as just the picture in the center does. So what Lime does, it will extract what part of your image had the most influence on your entire data set or your entire predictions, right? So that is one thing that we were using. Okay, if they are telling me that my handwriting is slant, it will highlight where my handwriting was slant. If it is telling me my handwriting has more pressure in this one corner, it will show it to me which corner that is and things like that, right? So that is the kind of explainable AI we wanted to induce here. Okay. Am I missing something? Yes, so for instance, Lime could highlight areas with well-defined strokes or consistent characters, spacing that contributed to an image being classified as valid or invalid, right? This level of transparency builds trust in models. I forgot to speak about the applications of this, right? So, of course, analyzing your personality is one application. Another application of handwriting analysis is our CID shows. People know the CID shows? Okay. So you get a piece of paper in a corner of the room which is probably written by the killer, and you get the page and you figure out, oh, is it, you do a handwriting match between the two, right? So there's like a lot of involvement of forensics here, forensic science here, because they could really use handwriting analysis, not just in identifying killers in very climatic way, but also in forgeries, check frauds, art frauds, all of these things. We can always come back and use handwriting analysis over there. What am I missing? Okay. Now, we'll move on to the results and evaluation of this one. Yeah. So.
The Lime model, right? How is it pre-trained? Because cat and a dog are like very, very specific objects. You have a particular shape. Can you hear me? Yeah. So the example that's given here, cat or a dog, right? It has a very objective shape, right? But with handwriting, it's like, we don't know, it comes in varied shapes, sizes, and the font, right? So what approach did you take to pre-train the model?
What approach did we take to?
Pre-train.
Okay. So again, like I said, we had those data sets. Now, the data set that we found online, the IAM data set, that came in with already characterized things that, okay, pressure is this much, maybe this slant is this much and all that. Now, based on that, we had someone manually go through all the handwriting pages that we had written, that we got the students to write, and mark them. So they literally sat down. We had a bunch of 3 or 4 students. They did this for 3-4 hours. They took each page. They had a obviously quantified version of what to mark what. And they basically numbered how much is the slant, how much is the height. We also had this entire separate project that was, that what it did was, say this is a line, it would take what is the top of this and the bottom of this and figure out the size of that, right? So we used that model to quantify how long or short or medium size, small size or long or large size the fonts are. Slants again was a visual quantification. If it's 40 degrees, 15 degrees, based on that we mark them. Pressure, again, what we did with pressure was the students had this. So again, it's not a completely foolproof solution. Obviously, there's going to be major biases here. But at the end of the day, we wanted to have something, at least a sort of data set that we could work with. So these students themselves figured out, so these were thin A4 size sheets that were given. Based on how much pressure the person's put is the imprint on the back of the page, right? So based on how strong the imprint on the back came, we quantified the pressure as well. That's how we built this. So building the data set, I think, was one of the bigger tasks that we had, because we had to put these students to a lot of manual work. And they were happy to do it, of course, but it's still a lot of manual work. So that's how we started. We quantified the entire thing. Yeah, I think that answers the question. Yeah.
The imprint on the back of the page, like that would depend on what type of paper it is, right?
Absolutely. So the papers that we gave out were standard.
Right.
Right. The one that came from IAM, the internet base, they already came up with the pressure quantification.
Okay.
Yeah. You can check out the IEEE data set for, it's called, I have it written somewhere, I'll probably give you the link.
Sure.
It's called IAM handwriting set, data set. They came with their own quantification of all these items. On top of that, obviously, the elements that we did not have there, we quantified by ourselves, right? So all the handwriting that we collected, we gave them the standard A4 size sheets, the one that we used for printing paper. Yeah, so those sheets were given out based on how thick or light the back of the paper came in, because it's just 2 paragraphs of words that these students have written, right? Yeah.
Nice, thank you.
Again, there is a lot of gray area here because, first of all, students are doing the quantification. Second, there is still the question of bias and diversity over here. And third, technically, handwriting analysis or graphology has not been considered science, but there's still a lot of research going on there. We're figuring out if it is worth putting in so much. Now, another huge functionality or advantage that I'd say of doing a handwriting analysis on early students or early kids is you can figure out if a person is going towards Alzheimer's or Parkinson's. Yeah, it's a very far-fetched thing, but that is another. So we had a collaboration with Nimhans as well on this. We basically gave them the combination of this and emotion recognition, which they would use on autistic people and people who are on a early onset, early Alzheimer phases, so that they can write. So the shake in their handwriting and all that, we wanted to do that. It's still under process. We have not gotten a definite result on it. Otherwise, I'd be more than happy to present that here. But that's still going on. We're still figuring that part out. Okay. Yeah, so the results, I don't think so. You can see here, our validation model or the test model came back with 97% accuracy. The pressure model came back with 95% accuracy. And we had our proposed model. We tried this on unseen data again. When this entire project was done end to end, we took a picture of our own handwriting in the meeting rooms and we uploaded it to the thing. It came back with around a 96% accuracy, but again, it's an accuracy that we thought is happening, because I did not think it was more than 30% of a slant. In fact, we had a good debate on this, where who decides what the accuracy for this will be, right? Who decides the accuracy for a new handwriting would be? Again, it will be either me or the person sitting in front of me who would quantify it. You can't exactly quantify. Yeah.
When you say it's hard to quantify these things, there are mechanisms, right? So, yeah. So there are algorithms or ways to quantify when you have manual testing or manual evaluations, right? So did you do any of that? Most common is when you take 3% and you calculate the evaluation matrix.
Okay, so we did, like I said, when we started collecting the handwriting and quantifying them, we had a set of algorithms that we ran on the handwriting itself, which would decide if the font size is small or big, or the slant size is 30%, 50%, things like that, that we had automated. We ran that automation on the results that we got. It was pretty similar, but again, things like pressure is something that you can't quantify.
No, I understand. So when you were assigning, let's say, pressure levels, right? So there are ways, like, let's say, for example, you'll create a subset of, let's say, 5 people who are going to assign. Then you're going to calculate how many people agreed with it, right?
Can you be louder?
I'm not audible. I'm audible now.
Yeah.
So basically, when you're manually creating a data set, right, and you have multiple people assigning any value, or let's say, like taking a simple example of classification thing, right, when you classify things. So at some point, you'll give it to, let's say, 3 reviewers or 5 reviewers, and then you'll calculate the matrix of how many people agreed to it, right, on the similar thing. So did you do any that kind of analysis to say whether your on the data set, whatever classifications that you assigned, how valid they were? Did you have multiple people assign on the same data point?
So I'll walk you through how the data set and the quantification happened once again, because I feel like there's a slight bit of a confusion. We went to these students, we gave them the same A4 size sheets, the printable A4 size sheets. All of them wrote a page, wrote the exact paragraphs that we've given him. Now these paragraphs were first run through the algorithms that we had written on figuring out what is the size of the handwriting, if they've written smaller versions, larger versions. We also had one more quantification where it would see the white space between 2 words and tell you if they have more spacing or less spacing, that and all was also a parameter. Pressure was one thing that we were slightly unsure of. One quantification was done through the students themselves, where they turned the page around, they saw the tracing, and they're like, okay, fine, this has more pressure, this is lighter pressure. But again, we had a system which was built, partially built to be honest, where the model, the logic itself will determine if the pressure is high or not. Personally speaking, I did not like the accuracy of the pressure analysis that was done. So when I say that there was testing done, I'd rather mix the manual testing and the person testing. Now once this data set was done, once all of the model is done, now we are at this phase where the thing is complete end-to-end. I have written the same 2 paragraphs. I have taken a picture of it. I have uploaded it to the system. The system comes back and tells me, this is the quantification of your slant, this is the quantification of your pressure and all that. Again, I will run that page through the logic of how big or small that is, how slant that is, how much pressure there is, how much pressure there is not. But because I'm not 100% confident in that algorithm itself, in the pressure algorithm itself, I am not going to be the one claiming that these numbers are right. I'm going to hold myself accountable here as well. I'm not going to be the one telling that this pressure analysis is right. We did give those sheets back to the students. They gave us a number, and based on all of these test cases together, we came up with this number. Right? There is a number, there is a 96.6% number, but this number is a combined test case of students giving a quantity and the algorithms giving us a quantity.
But for one data point, only one manual tester was present.
Sorry, one data
for
point?
each data point, let's say a data point is the written paragraph, there was only one person giving the final. There You did not go to approach of having
We
multiple.
had a four-student team who was running this, so I don't think so that was passed on through all four of them. Only one person has done that. Yeah. Okay. Any more questions? No. Okay. So again, results 97.4% we had on the validation model, 95.6% we had on the pressure model, and 96.6% on unseen data on the inputs that we gave towards the end. This is what my explainable Lime gave back to me. You see the red is where there is higher influence of those words. The white, if you see all the white spaces are left, right? So this tells you that these have not had more impact on my results, but this entire area has had impact on what my results have given me. Now, based on all these factors, again, these are just quantities that we've come up with, right? How much is the pressure, how small or big is the number and all that. Based on this goes through our process of, one second. Yeah, so this goes through a bunch of, I don't want to call, okay, they call themselves doctors, graphology doctors, they're doctors with PhDs. These people will run an analysis on what these numbers are, how much that influence you as a person, what kind of a person you are, and things like that, and they'll come up with a human analysis of you, right? So eventually, what the future, so the potential application in future work involves that. What we want to do is not just stop on these numbers. We want to put them in a system where they can actually analyze your emotional state, how stressed you are, how happy you are, how sad you are. We want to be able to do this entire thing where you don't need a forensic person to come in and do a handwriting analysis manually. You can just feed it into a system and that works out, right? So this model can be applied to document processing, forensic handwriting analysis, psychological research. Our future work will focus on refining pressure determination. Again, the one place where I'm very skeptical about how this is going to go. And exploring the use of large and diverse data sets. This is a minute aspect. Like I said, this is one aspect or one coin of a 12-part process, system that we're building. So handwriting is one part of the 12-part. We have emotion speech detection. Basically, while you're speaking, it will analyze if you're happy, if you're sad, if you're angry, things like that. That works out when you are trying to do a customer service, automated AI series. Imagine you're yelling at your Siri or Alexa, and then they respond in a very passive way, like, oh no, I'm sorry, this happened, right? So that is another part of that. Right. I am running out of time, so I'm just going to quickly end this. I have more questions? Yeah. Okay. I'm going to take questions outside. Yeah. All right. Thank you so much. I hope everyone